Alright, this is example 7.1.2. I thought I'd just kind of go between what they're writing down here and Desmos to look at the picture. So they say let's start with this particular quadratic form. So we have that quadratic form plus this something here that will is translating our conic section to the right or left and up or down. And so I went to Desmos, and there I have it plotted, and it's an ellipse. Now what we'll see later is we knew it was an ellipse because we'd already looked at that particular quadratic form and found it had positive eigenvalues, 16 and 3. And so that told me we had an ellipse. And we'll see more of that in later parts of the chapter. But so there it is. It is an ellipse, but you see it's been moved over. Here's the center up here somewhere, and it's kind of been rotated. And so what they're doing to understand the ellipse better is they are taking this part of the this quadratic form here, and remember, back here they had that form, and so there's the matrix for that quadratic form. Found the eigenvalues of 16 and 3. The eigenvectors, and I think when I did this I forgot to take the negative of x1 because they point out here that the determinant is of p is -1 when they use these two vectors. So if you just make either x1 or x2 negative, you get a +1 then. And so they did that. But there they had the eigenvalues and eigenvectors, and so here's their p that we got from getting the eigenvectors and normalizing them to be unit vectors. And so what they do is the coordinate transformation, they say, well, let's get new coordinates from our old coordinates. So in these coordinates xy, where are we here? Right, we have this ellipse that they're looking at, and so we want to undo that rotation, and so we do the transformation of p. So we say let x equal p times some x1, y1, and y be p x1, y1. So where they do that right here, so they get their x and y from taking our orthogonal matrix of eigenvectors and multiplying by these x1, y1, just those coordinates. And so when we do that and we substitute in, what should happen, and does if you go through the algebra and so forth, is it simply changes us to a non-rotated quadratic form. So we don't have that xy term in there. And you see we just got our eigenvalue 16, eigenvalue 3, and we have our plus here because both eigenvalues were positive. And so they substitute all that stuff into the original equation here. So even for this x and that y, they put it all in, they simplify, and you could use you could do this substitution with Sage Math, and we'll probably try to do an example like that. But not this one. I mean, not this video. Okay, so we see that we get this, and now we complete the square. Okay, now, so they got this, and so I plotted that, and notice that by making that substitution, what happens is we've unrotated the matrix. So that's what that first part did. That first substitution gave us this. Well, see, with that x and y term, it's still translated over here. Now, you don't necessarily have to complete the square to get this. Now, if I click on this, I can go up here and find the top. I can't find the sides. These are where it intersects the y-axis, not where it's the widest. But up here, I do have that, and so I get this, and so I could approximate this location here with minus 2.219. Now, another thing I could do is I can use calculus and implicitly take the derivative of this thing, find y prime, and I just need to find where y prime is 0. That's where the numerator is going to be 0, and where y prime is undefined over here. Well, if I do that, I get that it's y prime is 0 at x equal minus 8 over negative 13, which is minus 2.2188, and notice this is minus 2.219, so it's just rounded. So that was a very good estimate there. And here, when I check where the denominator of y prime is 0, I get y equals negative 1 over the square root of 13, and so that's this number. And if I plot x equal that, you see it does look like it's going right through the middle there. And y, this one's a little harder to see, but yes, so there's the center of this thing at that x and that y. And so I know how much this needs to shift is by those amounts by doing the derivative. Now they, though, so I'm going to turn those back off, go back here. So they do completing the square. They group the x1s together, pull out the 16. 256 over 16 is 16. And so they get this. For the y, they get something similar. They do completing the square, and they certainly don't show their steps a whole lot in there, but they took half of that number as their a here, so x1 plus a squared, and took half of that number. But if you add the squares of those in, you have to subtract them back out. And well, they moved the negative 31 to the right and they added them in here. So what they added in on the left, they added in on the right, and that simplified to 48. And so that means we could write this same thing I have plotted here in this other form, with the squares completed and so forth equals 48. So now they do another substitution where they pull those off. So they want the new origin to be at that spot. So they say let x2 equal what's in here, because then we'll get 16 x2 squared. Let y2 equal what's in here, then we'll get 3y2 squared equals 48. So they do that, and so then they have that, and so if we plot that, which I've got here, you see now that has moved it over so it's centered at 0, 0, and we can see the major axis here on the y-axis, the minor axis on the x-axis, and we can easily pick out this widest spot there and the widest spot up on there, and so as we look at that, we see that here this is the square root of 3, right? If y is equal to 0, I divide both sides here by 16 and get x squared equals 3. So this is plus or minus the square root of 3. And similarly, if I let x equal 0, divide both sides by 3, I get y squared is 16, or y equals plus or minus 4. And we see that that's what we have there. Okay, so we can use this eigenvalue method to get an idea then of what's happened to the ellipse. Okay, and we can undo what's happened to the ellipse and get it in this nice form so that we can understand maybe a little better. If I look at this, I can very quickly tell you the major and minor axes. Looking at that, not so much. Okay, so that's the kind of thing we've gained by doing this eigenvalue decomposition. So they say it reduces to this. Now, they just divided everything by 48 to get it in this kind of canonical form. And so they have it here, but of course notice no scale. They have the major axis going on the x. This is just a generic picture, and so they go through that idea so that we get the major axes here, and they point out that for this picture A is bigger than B. We don't have that, right? If I divide here, I'll get a 3 here and a 16 under the y, and so in our case B is bigger than A, and that's why it's taller than it is wide. And so they go through and get this final answer that they have. Let's see, and so here they are getting the axes here. So we had already found the how much these things moved, and then so here they're looking at this coordinate transformation here, and so they have the 3x minus 2y and the 2x plus 3y. So let's go back, find out where they had that. Somewhere up here. Okay, so here they have, right, they have x equals 3x1 plus 2y1 and so forth, and y equals this. They got that from x equals py. So let's go back down and look at what they have here. Notice here they have x1 and y1 in terms of x and y. So they've taken y equals p transpose x. Okay, so they did that. And then similarly, they had x2 in terms of x1. Okay, so they're just doing inverses, right? So they had, originally they had y as a function of, or xy as a function of x1, y1. Now they have y, the vector y, as a function of x, the vector x, the original x's. And then similarly, they did a transformation where they had, in one way, they changed out x1 for x2. Now, up here in their, notice here they actually had that in the same direction. X2 equals the x1, and so they are just trying to get x2 in the original x's and y's. Okay, so they found that inverse transformation from P transpose x, and here they get x2 in terms of the x's and y's. And the reason they're doing that is they're saying, oh, we'll let x2 equal 0. That's the, that's the origin in x2, and similarly they do it with y2. And what they're trying to come up with are these the axes that are going through the function, or sorry, not a function, the ellipse that's rotated. So notice they say that they have this x2 axis is given, x1 axis. The x1 axis, they're saying y1 axis, I'm sorry, I was looking at the x's and y here, but yeah, they're going with the y2 axis. That's where x2 equals 0, and so they're just, in terms of the original xy coordinates, when you're on the line representing y2, that's x2 equals 0. When does that happen? And they have it here, and they say, oh, that's this case. Okay, now that's defined implicitly. I don't know how well this will paste, but that's defined implicitly. Desmos doesn't care if it's defined implicitly. There we go. And let's turn off these other things, and you see, yep, that is indeed the axis. And coming here, highlight that one and do a Control-C and paste. And there's our x-axis, and so we can recover what these axes look like, and there's our center at -2, 1. Okay, and they talk about the center back here. Where do they talk? I saw it somewhere. They just looked for where x2, y2 were 0 and asked what that meant in terms of the original xy's. Well, okay, so they are doing all that right there, doing their substitutions and finding things that way, and you can find the intersection of these two lines and get that. So so that's an ellipse. Okay, so they were working with an ellipse, and those are the steps they're going through, and it is a way to get at what the heck you're dealing with here. So I've got this. It would be nice to know where its center is. Okay, so we got its center out of this. It would be nice to know its major and minor axes, what they look like, and there are these lines. And so this is just it's an algorithmic process to kind of undo the transformation that happened to the original ellipse. Okay, so that was, what the heck example was that? That was example 7.1.2.